Our last topic for chapter 1 is complexity. And it's a very rough measure of how long does it take on a computer to carry out a certain operation. It's something we'll be talking about throughout the course. Okay. So the way this works is computers store a real number in floating point format. Now, in this course, you don't have to know what that is, but what it is it allows you, it doesn't represent the number exactly, but it's very, very close. So for example, it wouldn't store the number 1/3 exactly as 1/3, but it would store it as like 0.33333 with about 15 threes in there, right? Which is, for all practical purposes, close enough. Okay, now, when you ask a computer to carry out a basic operation on two floating point numbers, like you ask it to add, or multiply them, or divide them, or subtract, now, that's called a floating point operation, and the slang for that is flops. That's a flop. A single flop is adding two numbers on a computer. Okay, now when you have an algorithm or an operation and you want to, what you do is the complexity of it is judged by simply counting up the total number of flops that you're going to need to do. So for example, you might count the number times you have to multiply two numbers, add two numbers, subtract or divide them. And you add up all those numbers together, and that's called the flop count for your operation. Okay, now, turns out this can be very grossly approximated because implicit in this is the idea that adding two numbers comes at the same cost as dividing two numbers, which is false. It actually takes longer to divide two numbers. However, still, this is just meant to give you a rough idea of whether carrying out an operation is going to cost you, is it going to be done in way under a second, a minute, an hour, a day? That's really what we're aiming for with this very crude estimate. Okay, now a crude approximation of how long it takes for a computer to actually carry out that set of operations or that operation is this. It's the number of flops you need to carry out divided by the computer speed. And the computer speed is given in flops per second. Okay? So you can see that flops you need divided by flops per second gives you seconds. So it tells you how long it's going to take in seconds. Now, this is very crude approximation. We certainly don't expect this to be even accurate within plus minus 20%. And in fact, it could even be off by a big factor, like a factor of 10 or more. But it does distinguish between seconds and hours. That it can actually do. Okay, now a current computer is can carry out around 1 billion flops per second. Actually, my phone can carry out 1 billion flops per second. So, my laptop can do maybe 10. But fancier computers, GPUs, for example, graphical processing units, they can actually carry out even much more than that. Some of them can even, actually many of them now, can actually carry out they can actually carry out 10 to the 12 flops per second. That's 1,000 billion, 1 trillion flops per second. That's called a teraflop per second computer. Okay, so let's just do a quick example. And let's say that you have an operation that takes, 10, that's going to require you to do 10 to the 10 floating point operations. That's a lot, right? That's 10 billion, okay? And so on a typical computer, let's make it a 10 gigaflop computer, but that means it can carry out 10 to the 10 flops per second. And so we would guess that that's going to take you about 1 second on that computer. Okay. So let's look at the complexity of vector addition, inner product. We can also look at scalar vector multiplication. All right, let's look at adding two vectors. So when we add two vectors, well, it takes n additions because you have to add each xi to each yi. And there's n of those, n entries. So that's n flops total. An inner product, that's calculating this, x1, y1 plus up to xn, yn. Okay, well, first you got to multiply all these pairs, and there's n of those. So you're going to have n multiplications, and then you're going to add them up. Now, when you add two numbers, that's one addition. When you add three numbers, that's two additions. So when you add n numbers, that's n minus 1 additions. So you're going to have to do n minus 1 additions n multiplications, and altogether 2n minus 1 flops. Now, no one would ever give the minus 1 because it's understood that this is very crude, and so people would always say that an inner product costs 2n flops. In fact, a lot of people would even just say n because we're not even shooting for a factor of 2 in accuracy here, just n for the inner product. Now, incidentally, this is interesting. Now we can say something about if one of these vectors is sparse, that can be a whole lot less. For example, suppose x is sparse and y is not. X is sparse means that most of its entries are 0. Now, when I calculate an inner product, I don't have to worry about those entries because all I'm going to do is multiply xi, which is 0, by yi. Doesn't matter what y is. I don't have to do it. So it turns out the only thing I actually have to do is for every non-zero entry in x, I have to multiply that xi by the corresponding yi, and I have to add those up. And so the complexity is around this. It's twice the number of non-zeros in x, right? So this is an example of why you might be interested in or care about sparse vectors.